Okay, so now we're ready to look at our second player in the study of motion is velocity. And this is a very important one, right? Because finally we get to understand how fast something is moving. So roughly, velocity means how fast is something moving, but this is a layman definition. This is not a rigorous definition, right? Because if you want to be able to measure it, then you would be asked, what do you mean by moving? You can, moving is not a precise word, right? So part of this physics course and part of your physics education in the next couple of series in Physics 3, one goal is to learn the way physicists think. And one of those ideas is to be able to make something vague, precise. Okay, if you can make something vague, precise, that's basically what science is about, right? So the whole physics training, even if you forget all about physics in the end, hopefully you've learned the philosophy and learned the way to think like this. But I mean, this is a good way to train yourself. So let's start with this. So let's think about, there's two words we need to make more rigorous, right? Fast and moving. So let's deal with moving first. Maybe we can say, instead of how fast something is moving, because someone's running and you go like, how do I measure that? This person is running fast and that's slow, but how do you measure it, right? So we can say how fast did something move from one point to another point, right? Let's say from, let's analyze things in one dimension first, all right? So we'll have one dimension. Let's see if you can see that on board, just barely. That will work with that. So from point x1 to x2, in these 2 points, right? Let me write this, x1, x2, before I get a better pen. So how fast did something move from x1 to x2? Okay, x1 to x2 I can measure, right? I can, as long as I have an axis and an origin. Remember how to describe position, you need a system and an origin, right? The zero is somewhere. I'm not going to draw it. Maybe I will, just to add completeness, right? That's positive x that way. Okay, so from x1 to x2, I can measure x1. I can describe position in one dimension, which is easier than 2 dimension. 2 dimension, you need a position vector. In 1 dimension, you just need a point to x2. But we have a name for that. When something moves from x1 to x2, it's called displacement, right? And that takes into account the direction as well, because if you go from x2 to x1, that way, then if I say displacement, then you will either say it's a negative how many meters if you're in 1 dimension, or you need to put in brackets, put in parentheses, describe the direction, left or right, like that, right? Okay, so how fast did something move? So how fast is, well, let's measure that with time, right? So if the time, if the clock is at t1 over here and t2 here over here, then I can rephrase this to how much time, because this is something I can measure, right? How much time is something I can measure, and how much displacement is again something I can measure. So now we've made something that is a vague concept of how fast into something that's measurable. All right, let's put this in an equation, right? How much time did something move for how much displacement, right? So I propose, this is the idea. So velocity, we'll have it formally defined as the amount of displacement over how much time, and I'm going to call that time taken. So the time taken for that amount of displacement. Okay, so as you know, as mathematicians, we're lazy. So let's write this in the equation and invent some symbols for it. So I'll use v for velocity, and amount of displacement. I can either use s or delta r, like that, right? So I can either do this over the time taken. So what's the time taken? So I need to subtract t2 over t1, right? So that's t2 minus t1. That's x2 minus x1. So I can write that as, let's actually do that. the delta x, right? So that's change in x, change in position, that's displacement, and the amount of time taken. And that's the velocity in the x direction. And if we want to generalize to 2 or 3 dimension, then we will use the full displacement. Then I will have delta r, delta t, like this. And since this is a vector divided by a number, that just means a number, multiplies in, or a fraction multiplies into the scalar. So that will give you a vector as well. All right. So in 1 dimension, you can have this. In 2 or 3 dimensions, you can have that. Just to be clear, we can write this as Vx, Vy, Vz. And that's defined as 1 over delta t dx, or delta x, delta y, delta z, but this gets multiplied in, right? So it's delta x, delta t, delta y, delta t, delta z, delta t, like this. So Vx is equals to delta x, delta t, and that is a special case. Sometimes we'll do, if you need to deal with the y direction, you don't have to reinvent the wheel. You can just take Vy is delta y, delta t, Vz is delta z, delta t, like that, okay? We'll rarely deal with 3 dimensions, so I'm going to erase that, but you get the idea. So this is a little bit just for reference over here, but this is sort of the essence of it. If you understand this, that is just a simple generalization about it, which we won't talk about too much in this course. Okay, of course, you can also, if you like, this is identical to writing S over delta t. Okay, S being the displacement, let's say, just to be clear, the displacement in x direction. If I'm being explicit about my directionality. Okay. All right, but now I want to point out one point. Is this? So let's look at the motion on a graph, because I have x and t at the same time, right? So let me put the x-axis here and the t-axis here. Okay, so I'll mark x1, x2. So these 2 points over here, and t1, t2. Because I want to be able to look at this equation and get a sort of a more intuitive sense about how it looks on the graph. So at first, at time t1, I'm at this point, and then at time t2, I'm at this point. So this is how I moved. But did you notice no one says I moved in a straight line like this, right? So I need to address that issue. Did I move sort of the same speed all the way, or did I move very slowly at first and then speed up? How do I know that is slowly at first? Because look, if I sort of draw a point of a line over here, the first part over here, I didn't really move a lot of x, right? I just mainly stayed really close to x1. And then in the second half, or the second part of t1 to t2, suddenly I went from just a little bit above x1 and shot right up there. So here, I moved a lot of distance in a short amount of time. Here, I didn't move too much distance in a long amount of time. Okay, so what does this tell you? It tells you velocity seems to represent it has something to do with the slope of this graph. All right, so this is a famous graph we call the XT graph. Okay, or in full name, position time graph, but we're lazy. A lot of people will just call this the XT graph or YT if you're looking in the Y direction. But yeah, in general, position time graph. And it looks like I noticed something, right? Let's write this down. The velocity is represented by the slope of the on the XT graph. So velocity is the slope on an XT graph. Okay. Now, is this a new information or old information? I would say it's old. It's not new, because once you have this, that just follows from this. Why? Look at this. This is delta x, delta t, right? So the change in x, let's keep that. I'll use that in a second. But let's draw in red. This is the change in x, right? This is the change in t, right? So what that means is this is rise over run, right? How much do you rise over how much you run? That is precisely the definition of slope. So this is not a new information, but just an interpretation of this formula. Okay, so I'm going to draw an arrow together, and you can see that as long as I have a definition, so this is right definition, then it's just the slope of that. Now, there's also now we need to think about. Still, I haven't addressed the fact that which does it go in a straight line or like this? All right. So what we mean is the one the straight line like this has a constant slope, right? And this one has a varying slope. So this one with constant slope, it means constant velocity. So the straight line path, when I go like if you see a path like this on the xt graph, it means that it's moving at a constant velocity. And whereas the second one over here, this is not a constant slope, so it's a varying velocity. In fact, you have a higher velocity at the end and a smaller velocity at the beginning. Okay. All right. So one last thing to note is that this is actually because if I just use delta x, delta t like this, I cannot tell if the velocity, so if I just use this, I can't tell if this is going at constant or at varying. So what I actually defined is actually just an average, okay? So what I've defined over here is just the average velocity. So let's put, let's write that as Vx comma average. If you can squeeze that in, I'll just enlarge this so you can see Vx comma average. Okay, all right. So that just tells me the average velocity. Well, if it's constant, notice if the average is the same as at every instant, because at every instant it's the same velocity. So the average velocity is the same as the instant velocity or instantaneous velocity. However, here you see that at this instant, it has a lower velocity. At this instant is a higher velocity. So how do I define? So the next question is I also need to define Vx instantaneous. Okay. I'll keep my color scheme consistent. All right. So I've defined average velocity and instantaneous velocity. So drawing from this inspiration, I should define, right, so this is average velocity. So that's average slope. And if I now want instantaneous velocity, it should be the instantaneous slope on the xt graph at a point. Okay, very important, right? So if I'm looking at a velocity at this point, I need to look at the slope at this point. Okay, so that's the difference. How do we, so that's the concept, that's it, right? The only thing left to do is to find a way to write this mathematically, okay? And now to do that, we will need the idea of calculus. Now, but don't worry, usually when we say this word, usually people get really scared, but the concept is actually very simple, okay? I'll show you what I mean. So I will enlarge the axis a little bit for us to be able to see easier, all right? So xt, right? So let's say it's you start from somewhere yeah, some random starting point, and you move like this, okay? So let's say you start from here, move to there, okay? So first, just to check if you understand the concept clearly, is the velocity getting faster and faster as I move through time, or is it getting slower and slower? Well, let's pick a time segment. Let's say that is 1 second from here. Well, here it didn't cover too much x. right? So it's moving at a slow velocity. Here, it looks like it covers more x, so it moves at a faster velocity. And then when I get to the end, look, it covers a lot of distance, a lot of displacement from just a little bit of time. So it's getting faster and faster. All right, so the velocity, is it constant? No, it's not constant. If the slope is constant, then it means for every second, can you see that, right? For every second, if it's that it covers the same amount of height, right? The same amount of x, then you have a constant velocity. Okay, so first thing we know is the velocity is not constant. So what we can do is find the average, right? So you can just take the initial point, the final point, right? So you can take initial, final, find the heights, right? And then time initial, time final, like that. But what if I want to find the velocity at this instance, like this? Okay, so I need the instantaneous slope at that point. So I need the slope exactly at this point. So what you need is to take out a ruler and draw a tangent like this. So that tangent over here, right? This, right? If you calculate the rise over run over here, that will represent the instantaneous velocity. Okay, but how do we write this mathematically? That looks like a lot of words because I'll need to write basically is the tangent, right? So I will replace the word instantaneous slope to tangent, right? The tangent on the XY graph at that point. So the tangent at that point. And maybe let's say the slope of the tangent. Slope of the tangent. Okay. But as you can see, we don't want to write too much English. We want to try to find a way to capture this information. And here's the genius of calculus, right? Hear me out, right? So you start from here, pick a point from here somewhere else, all right? So let's say, let's enlarge the scale, right? So let's say from here to here is 1 second. So I'm interested in the velocity here. So this is, I'm interested in the velocity at this point. First, let me take, let's say at this point it's t. So t initial, t final, but this point is just t, and this point is t plus 2 seconds later. Okay, all right, I can take the average velocity. So if I take the average velocity, I'll be taking this distance and this time up to T2 over here, right? And I'm going to calculate this slope. Well, clearly that's not what I want, right? I want, I'll use red over here, want the velocity at this point. Okay, so basically I want the slope, the red slope over here, but the black one over there is not the same as, just I'll erase some of these to keep the diagram simple. The black one is not the same as the red one, right? So if I take the average velocity 2 seconds later and take the distance it traveled or the displacement it traveled through, divide by 2 seconds, then it's not gonna be the same. How can I improve my estimate? What if I take 1 second later, right? So instead of t and t plus 2, let's say I take a delta t, a change in t, instead of 2 seconds, I change 1 second and draw a line over here. Not very straight. Let's try that again. A straight line like this. Okay. Can you see that the second one is a better approximation to the red one? The red one's what I want, right? It's the tangent at this point over here. Okay. And if I take t plus 1, it's better. What if I pick t plus a half? That's pretty close, right? I can't write further more on it, but the idea is half a second later, 0.5 seconds later. If I take the average velocity for that, right? So if, let's conclude this, right? If I take the delta x when delta t is 2, it's a very bad approximation. But when I take the delta x when delta t is 1, I get a better one. When I take delta t is 0.5, I get an even better one. So you can see, I won't start drawing this because it gets really, really small, right? You can zoom in. if I keep moving this point closer to closer to t, like this, right? So if I pick, for example, 0.1, like 5 times less, that little line is almost coinciding with the red line, right? The red is what I want. I want the instantaneous slope, right? I want the slope at that instant. So if I can find a way to get t all the way to 0, that is the instantaneous velocity. Now, in practice, it's very hard to do, but the concept is clear, right? That's what you want to do to get the exact tangent, okay? What you need to do is first make a poor estimate, and then make your delta t as small as possible, okay? And when you get to 0, then you've got it. That is the instantaneous velocity. And how can we write this in math? We could, and we absolutely can. And mathematicians use this symbol. They say, well, it's delta x delta t. You make an approximation, but that's not very accurate unless if you want the instant, you take the limit when delta t goes all the way to 0. And once you take that limit, so you take the limit of the average, so this is the average velocity, right? In the x direction. Let me not write the x. You take the average velocity, but then you take the delta t, right, all the way to 0. All right, and that will give you the instantaneous. Whether this is easy to do or not in practice, that's a different question. The concept is encapsulated in this equation. Okay. All right, understand that? Let me rephrase that, right? Or let me summarize that. Vx, average velocity, is just basically the rise over run on a position time graph, on an xt graph. But the instantaneous one is the rise over run at a single point. So you can't really do it at a single point. So you take a little bit further, right? You do take some delta t, you do take some run and some rise, and then you shrink it all the way to 0, right? That encapsulates the idea. So every time, we'll worry about how to do this in practice in the next video, right? But the concept will clarify. We'll want to understand that first as our goal of this video. You see that even in practice, it's relatively easy because we're dealing with a very special and simple case. But we'll get to that. Don't get ahead of ourselves. Understand the concept. All right. Last thing to say is we are lazy people. So we don't want to write this chunk of mess every time. So we invent another symbol for this ugly chunk of thing is dx dt. And you might recognize and see this a lot of times in calculus, right? So this is the idea of calculus. So comment number 1, just again, because I use a lot of shorthand in taking notes, just to make sure you know that the equal sign of 2 dots means definition. I'm defining a new concept with something complicated, but essentially old concepts, right? You know what does delta x delta t mean? I introduced a new concept of limit, but I've described it already. So I'm defining, this is just basically this. And this symbol in mathematics means identical to, right? Translates to identical to. And I'm using it here just to emphasize that this is basically a lazy way. It's identical to this, right? It's just a lazy way of writing this. Okay, that's comment number 1 about notations. And so make a note of that. Erase that for clarity. Comment number 2, just to summarize, I keep saying this is calculus. And what is calculus? Calculus is basically the idea of dealing with curved motion, curved graphs, curved things that changes all the time. And obviously in daily life, things changes all the time. That's why calculus is very, very useful. But at the heart of it, you basically understood the most difficult thing in calculus already, this concept, okay? In practice, basically there's just a bunch of rules you follow, and we'll see that, but we don't even need calculus for 99% of our course. Certainly not for the next video, and I'll tell you why exactly that is. All right, so average velocity, instantaneous velocity, that's the concept, and we'll look at essentially that's the amount of displacement per over the time taken. We'll look at acceleration next.